All right, so we ended last class with onion routing. I ended on a think, pair, share. So I'm going to do a really fast move up to that think, pair, share. And we're actually starting today with a think, pair, share. Onion routing assumes this model. After going through enough of your midterms, I'm convinced a lot of you do not understand networking at all, even at the level I expected you to start the class with. So the ones that were assuming really basic networking knowledge were the most devastating questions. An onion route is a network on top of a network. So what's happening in an onion routing situation is you are creating a fake network on top of the internet. In this example, you have a client who's sending a message to node A, which then sends a message to node B, which then sends a message all the way up here to node C, which then sends a message down there to node D. Oh goodness, this is not optimal at all. But when you see me draw it as a graphic, I almost always draw it this way. Right? This looks totally optimal, right? We just go from client here to node A, to node B, to node C, to node D. That's nice and straight. But what's functionally actually happening is that we've created a fake network called a Tor network on top of the real internet, which is itself, all of these little clouds here are all also networks. So we are actually, when we're dealing with networking, we're frequently building things on top of other things. This is the last step I showed you with the Tor network. So when we build a Tor route, we do it iteratively. We build a route to node A, then we build a route to node B, then we build a route to node C, and this is the last step where we build a route to node D. In this route, what we do is we start by we here, I mean the client device. So the client device starts by creating a message, M up there. M includes the D session key, a symmetric key. This might also be the initiation of, say, a Diffie-Hellman key exchange, but it's basically the session key. It goes and takes the public key for node D, and it encrypts M with it. And then it takes that M and it encrypts it using the session key for node C, and then it encrypts it again using that result for the session key for node B, and then the session key for node A. And then it takes that fourth message, the final kind of layered message, drops it on the network, and sends it to node A. Node A then decrypts it. It can decrypt it because it's got its session key, doesn't it? So it decrypts it using the session key, and it goes, I have an encrypted object. I shall send it on to the address it says. Drops it on the network and forwards it to the B address. Node B then decrypts it using their B session key and forwards it on to the C address. Node C decrypts it using the C session key and forwards it to the D address. And node D decrypts it, and now it has, and now they have the D session key. Now all the nodes have this state. Each one of them now knows the node they're getting it from and the node they're going it to. Now I have annotated this with things like exit node D and client device. But from the perspective of each of these devices, everything here is a node, including the client device. So here, A, for example, knows it's getting its input from the client, and it knows it needs to send its output to B, and it knows its A session key, and that's it. It does not know the rest of the path. It doesn't even realize that client is a client. It just thinks the client is another node. And this is true for the whole rest. All right, we have now set up our route. Now that we have a route, we'd like to send some traffic along it. That's the whole point of doing this. So in order to send traffic, we start by creating our message, whatever the message is. It might be something like load a web page or whatever it is. And we take that message and we use our symmetric key encryption of the message and the destination address, the place we'd like this message to go. And we take the D session key and we encrypt it using that. We get message 1, then for message 2, we encrypt it using the C session key. For this one, again, symmetric encryption, we use the B session key. We provide C's address. Here we do A session key, we provide B's address, and then we send that final one, M, which is now this layered encryption, to A. We do the same thing again. A decrypts it using their A session key. B decrypts the next one using their B session key, sends it to C. C decrypts it using the C session key, sends it to D. I know this is sounding boring, but it's going to be hard in a minute. And then D decrypts it using D session key and then forwards it to the destination. All right, this now we hit the think, pair, share. Fill it in backwards. I'm going to give you 1 minute to think about that. So get out paper or the equivalent. Try to fill in this slide. I have very purposely not provided the answer in your slide decks. All right, go ahead and talk to your neighbor. Or go ahead and talk to your neighbor. I'll add a simple fact. We have hit the point in the class where often the answer to these questions is sitting in both this slide deck and earlier slide decks. So to solve this, you need to think about stuff we've already learned and what we learned today. So go ahead and talk to a neighbor.
You can implement this such that the client also that's why you ask the client. Yes, we know it.
Like you're making sure all the packaging and everything. Yeah.
The server has to send the certificate out to you.
Whatever they're sending to each other.
But how they have a so
All right, sorry, I'm coming back center. I think I was over by a minute because I was talking to a bunch of people. All right, let's go down through the middle of these things. So first off, why does TCP need to happen first? How come we can't just dive right in and do TLS?
It's on a lower layer.
Huh?
It's on a lower layer.
It's on a lower layer. It is on a lower layer, but that's not good enough justification. There's more reason here. First off, TCP is not the only thing that can run. It's the one I'm focused on in this class, but you could also be using UDP, you could be using, there's other approaches. TCP I bring up because it's used here, and it has a feature to it that is important. It establishes a channel. What do I get from a channel? Why bother with a channel? Because UDP does the same thing with no channel.
Deliver the packets if they are lost.
Reliability. TCP gives me reliability. What's going to happen on this network? My message is not going to go across as one nice block, is it? No, the lower layers of the OSI model is going to just like machete break up my message into pieces. If I have done a good job with encryption, what has happened? I have had information diffusion. So my little A that I originally was in this message is now the information from it is spread across every single packet. What happens if a packet gets lost? My message cannot be decrypted. The whole thing's toast. I need reliability. I need to know whether or not every packet got there, and I need to make certain they all got there. And so in order to support encryption, not necessarily the protocol itself, because you might notice if the packet doesn't come back in the protocol, but the resulting messages that I send across, I need reliability. I need to make certain that the entire message gets there. So we do TCP first, and we build on top of TCP instead of something like UDP, because we want the reliability. And we want to make sure that packets are getting there, and we're not losing any. All right, second one. What parts of this exchange are public? Publicly visible. Staring at the rest of the class. You can't just let the front and the back row answer everything. I mean, this is the easier question, which is why I'm poking you guys. And I know I talked to people who knew it.
The TCP.
So TCP is most definitely public because TCP has no encryption.
Client hello and server hello.
Yeah, so this original message is entirely public. That original message is entirely public. And then the last kind of finished message is encrypted because it has to be to kind of do the proof. That means that all of the key exchange is happening in the public. Now, this is a bit weird, actually, because this message that is now on the screen here actually does have a bit here that's encrypted, right? Because the server explicitly sent a digital signature. Digital signature is fancy language for encrypted with my private key. But who can read a digital signature? Everyone in theory. Definitely everyone in practice, because it's sending its SSL certificate, which contains its public key, right next to the encrypted thing. So we kind of assume the attacker has access to the whole message. So everything here is basically unencrypted except for the last step. And the last step just contains done, not actually any important information. All right, so in theory, a man in the middle is not possible. If everything was public, why isn't it possible to man in the middle of this connection? On all of your website, like you're sitting there on your computer accessing websites, it's all protected like this. So we really want this to be not man in the middle, not to have that ability. What is stopping a man in the middle from happening? I know everyone was scrolling up and down the protocol a minute ago. Like, what did you find that might stop a man-in-the-middle attack? How do I stop man-in-the-middle attacks? One of them is encryption, obviously. I just dropped some encryption on there and the man-in-the-middle can't attack it. And up till now, we've just been treating it like magic fairy dust. We just put the encryption there and poof. But now we have to set it up between two strangers. So how do I make sure I don't have a man in the middle? What's stopping Bob from just saying, here's the key this way, here's the key that way? There's a very explicit step here.
Client verify the certificate in
The
public.
certificate. Yeah, no, you're very much correct. This message from the server explicitly states its SSL certificate, which contains its public key, and a digital signature, which is proof that it has the private key. And then the client verifies both of those. It says this is actually the public key according to the signature, and the signature is valid from a CA I trust. And it verifies that the server is able to encrypt really anything using that key and produce an output. Because of that, it's only possible that the client is talking to the server. And they must be talking directly to the server because a man in the middle could not create a different message and send it. That this signature is incredibly important because it's how the server is proving that you are speaking to it and no one else. All right, this is how we stop a man-in-the-middle attack. Let's say I'm a well-financed attacker. I have a lot of money. Maybe I'm a government. Let's just pick on a government. Let's say I was a government and I wanted to do this. How would I do it anyway? How would I break in?
One way would be to literally break in at the CA. So using a CA or coercing a CA or something to give you to sign whatever you have so that you can basically inject yourself.
I get a fake CA certificate. By fake, I mean a real CA certificate that should never have been issued. I as a large government, walk into a physical CA office that exists within my country. I plop down some sort of official-looking order, and I say, thou shalt now sign this certificate that says I am Microsoft, even though I am not Microsoft. And now I have the ability to sign things and give a certificate that is wrong, but verifies. And this is one of the most common ways to man in the middle of this.
You have authenticity guarantee for the server, but you don't have authenticity guarantee for the client. Is there any implications to that?
It depends on how much you care about the client. So again, security here is frequently done in a lot of layers. The question is basically, we can prove the identity of the server, but we cannot prove the identity of the client. This is true. This method will only tell you whether or not you're really speaking to Wikipedia.com. It will not tell Wikipedia.com who it is speaking to. Now, the way this is set up, and I don't want to work through more detail, but if you really do work through it, it's not possible for a client to end up speaking to a fake middleman and then speak to the server. You can kind of go through what I have presented and work that out, but it's not possible. It is entirely possible, though, that the server thinks they're talking to Bob when they're actually talking to Alice. They just can't be talking to Alice, who's then talking to Bob. So Bob knows who they're speaking to. Usually servers solve this via this thing we call login. So you set up an encrypted connection. Now we have encryption. You know who the server is. The server does not know who you are. So they helpfully pop up a login screen and say, will you please log in now? And that's how they do the inverse of that side. But it is not part of the protocol. All right. We all still kind of with us here. This is kind of the point I just made. Certificates are vital. You kind of have one version. One version is where they sign something they shouldn't have signed. The other one is when they forget to renew theirs. So this invariably happens every time the U.S. government shuts down, that some of their web pages just break. And what happens when it breaks? So what happens when your browser is given a certificate that is valid but has the wrong date on it?
It doesn't work.
Well, your browser will usually throw a fit. It'll pop up something and say, it changes every year what the browser says as they keep changing things. But it basically pops up a fit and says, either this is an untrusted site or this is a certificate that's out of date or something like that. This is a massive problem for us because if users learn that clicking through those dialogues is a perfectly reasonable thing to do, all of the stuff collapses. And so, anyway, this is one of the problems that can happen. And I'm just throwing this on here to make a point that often we're dealing with layered encryption. When we say a connection is encrypted, usually we mean TLS, but there are so many ways we can encrypt a connection. The application itself could encrypt it. I mean, I can go and run a piece of technology that uses my private key to encrypt against a public key, and then copy and paste that encrypted text into an email and hit enter, right? The application itself could encrypt it. TLS could encrypt it. You could be running TLS over a VPN, which is now helpfully also encrypting it. There's nothing stopping that physical layer from being encrypted as well. If it really wanted to, a big network server could just take 27 million packets, put them all together, encrypt them, and send them across the wire. I have seen discussions of things like bits of India, which are badly connected, and actually just setting up a bus, for example, that literally just connects people in batches, in which you send a message over the bus, and then when it comes within range, you can connect, and when you can't, you can't, and then it just slowly does very slow networking. You can do all sorts of weird stuff. Encryption is usually layered. We are looking effectively at the Swiss cheese model. If the application really doesn't trust the stuff under it, it may encrypt stuff itself. You're using things like TLS to do the network connection, but maybe you're also using it because you don't trust something else to have done it right. You're using the VPN because you don't necessarily trust the websites to have done this correctly to begin with. And you just kind of layer a lot of networks. So you do frequently end up with a situation where one technology is sitting on top of another technology and on top of another technology. There is no reason you can't run a VPN over Tor. You can do it.
It'll be very slow, but you can do it.
It would be very slow. Each additional layer does add latency. And this is one of the biggest reasons people don't do things like create a 10 node deep Tor network. I think it's 3 is the recommended. Because it starts getting slow. But yes, these things layer. Networks on top of networks. All right, this is TLS. I'm now going to switch again sideways. Sorry, this is kind of like the mop-up lecture where we're starting to actually talk about security, but security unfortunately happens across all sorts of spots in the network. So we're like here, and then we're there, and we're there. We're bringing a lot of other content together, but it's just a jump. Any other questions about TLS? I'm going to go start moving over into denial of service. Up until this moment, we have been treating the network as really trying to create accessibility. When we talk about security, TLS is trying to do a confidentiality. It's sort of trying to do integrity. It's sort of trying to determine who you're speaking to. TCP is doing things like trying to go and create accessibility. So it's trying to make sure when you access something, you'll get all the packets back. One of the big things an attacker can do is attack accessibility. Denial of service style attacks, of which there are a lot, focuses entirely on accessibility. The intention here is to usually take the target down. So the idea is you have a web server out there. If it stops running, no one can get to it. Perfect accessibility attack. If you do not like something, you maybe just want to knock it off the internet. Common thing. Keep in mind that in order to do denial of service, you do not necessarily need to take the target down. In my dorm when I was in undergrad, it was a common thing to hear Counter-Strike played the entire length of the hall. And when somebody didn't like somebody else, they would just launch a ping attack against it, which will slow their network connection down. And if you're doing a live shooting game thing, then when it gets slowed down and your rate's bad, you start dropping in your quality ability of doing stuff, and we have a denial of service attack even though you have not fully taken the target down. Think of that also in terms of, say, a remote heart surgery. Let's say you wanted to kill somebody, and you know that they are going through a heart surgery in which they are here and their surgeon is on the other side of the planet. Much more devastating, same principle. So denial of service is usually about stopping the web server or stopping the client or in any way stopping this connection. either by massively slowing it down or cutting it off entirely. So this could be things like cutting power cables, very effective. Overloading the server with invalid traffic, just send it garbage that it has to deal with, and now it can't deal with the other stuff. You could remove someone's user account. When we were talking about passwords, we briefly mentioned doing things like lockout to stop the attacker, but the attacker can also use lockout to lock the user out, which is the denial of service attack. You can also remove, you can change the DNS point. I have that on there, but I think I used to cover DNS earlier and I won't cover it for a while now. So you can do that too. But ones we're going to talk about briefly are SYN flooding, spoofing, and smurfing, and I'm going to go through these. These are all network-based attacks. Syria, the example we had before, again, this is a denial of service. You just disconnect the internet from there. No one can access Syria. Syria can't access anywhere else. Denial of service. So this is standard network. Here we have the attacker. We have a victim server. It's entirely possible for the attacker to just send a message across the internet to the victim server. They can do that. Anyone can do that. That's the whole point of a server. So one really basic way of attacking someone is using TCP. So you notice in TCP we have this SYN, ACK, and then finally there's a fin at the end of the connection. Do I have to do all three of those? What happens if I only do one of them? So the idea is that Alice just sends a whole mess of SYN connections at the server. The server has an internal table. It has to have an internal table about all the connections it's currently managing. That table is finite. It's large, but it's finite. And if I just fill it up, what happens to the next connection that comes in? It gets dropped. So that looks, broadly speaking, like this. So that's a singular SYN. And then this is a singular ACK back. But in a flood example, a whole lot of SYN messages all come at the same time, and it just starts filling up this connection table. And it is finite. Now when the next message comes in, can't access it. This is exactly what happens when, say, Taylor Swift announces, FIFA is our current example. This is entirely what happens when FIFA announces the tickets and everyone tries to access the same webpage at the exact same time, except for that's not actually an attack. But the outcome looks identical, which is that now there's all the number of TCP connections the server can handle, gets filled up, next connection that comes in gets dropped on the floor, and does not get a full TCP connection even set up. It's not even the case that the page starts loading because it can't even create the TCP connection. And this is called a SYN flood. So there's some problems with the model I've just shown you. The first one is attribution. So when I sent those SYNs, they had my IP address on them. And the last thing you want as an attacker is to have your own IP address helpfully written on all your attack messages. Bandwidth. My bandwidth as a home network user, or really anyone that's not a backbone server, is a lot smaller than that server's. So if I flood my home network server with these packets, I'm barely going to bother that big network server that has a huge trunk and a massive bandwidth. So you can do this if you're, say, one Counter-Strike person attacking another Counter-Strike person inside of a dorm over the same network, because your computers are roughly equal in power. But if you're a little laptop and you're trying to take down a server this way, the server's got more memory and more bandwidth and may just not be able to even impacted by this. So we introduced spoofing. We talked briefly about how there's no reference monitor on the internet. So what is there to stop you from lying about your IP address?
The internet police.
Yeah, so there are no internet police.
Well, in China.
We'll kind of get to. Okay, I'm going to set that aside. So now the idea is that, so the other point I guess I failed to mention is in SYN flood, one of the other problems is the bandwidth is two directional. So I send a SYN message and then the server is going to send an ACK back. So now my connection is being filled with SYNs and ACKs, which means I can only use half of my bandwidth while doing this attack. So those acts themselves are also problematic. So when I spoof, there's some nice advantages. One, now my IP address isn't written on the attack message. That's nice. Two, if I send a SYN out, the act's going to hit a different computer. I now get 100% of my bandwidth, and some other computer gets hit with these random acts that it doesn't even know what to do with. The biggest problem with this, which is in reference to the comment on the side, is what we call ingress filtering. So the University of Waterloo, just to pick a random example, would really rather not to have a bunch of attacks originating from our network. We consider it bad publicity. So it's really easy for our border gateway network, our border network, to go and say, I see a packet coming across. It's got a from address on it. Is this one of our addresses? Oh no, this isn't our address. This is the address of the US government. Why on earth is this originating from the inside of my network? Drop. We call this ingress filtering. So the idea is that if you send a message across these routers inside of our local network, when it bridges to the outside internet, it stops and goes, is this from us? And if it's not from us, it drops it on the floor. Now, what I've just described is good network behavior, not necessarily something that is required. So some networks will not do this, and some networks will do this. My guess is this network does it, and please don't check. But the idea is this will stop an attacker from, say, a home network. So like Rogers Internet would totally do this because they just don't want to deal with the garbage from the problem. And it's an easy thing to check if you have the network set up appropriately. This makes spoofing hard to do. And that's a problem if you're an attacker because you really want those benefits I just mentioned. So we do something called smurfing. So smurfing is a reference to a TV show that I don't even know if you know about anymore called The Smurfs, in which everybody just looks identical. And there's a lot of them. And sometimes they solve problems by just throwing a lot of people at it or a lot of Smurfs at it. And that's the idea here. So a smurfing attack exploits a protocol called ICMPs, or Internet Control Message Protocol, whereby remote hosts respond to echo packets saying they're alive, also known as ping. So the way ping works, if you've never used it, is you just type ping and then the address, and it sends a very small packet at the destination server, and then the destination server then sends a packet back to the host. Or sorry, back to you, saying, yes, I'm alive. So it's this question, are you alive? Yes, I'm alive. And you send the message back. This now means that the packet I send is much smaller than the packet I receive. So I send one packet, I get back 27. Because this is how ping works. So that's kind of nice, but I still have a lot of those same problems, right? My bandwidth is still quite small. The victim's bandwidth is quite big. But what am I going to ping? Because most of you have probably pinged another computer, like a specific computer. Maybe you ping Google to figure out if your network's broken. What if it happens if you ping an entire local area network? So you can sometimes ping a gateway router, and the gateway router will helpfully send that ping to every computer on your local area network. Every computer on your local area network then does what? It sends a response of like 10 pings back, because that's how ping works. And now I have 10 times the size of the local area network traffic coming back. So now if I forge my source address, so I change my IP address, and I send that, I lie, and I say my IP address is totally Wikipedia's address. I write that down. And then I send that ping message to the local LAN. And now the local LAN helpfully responds to Wikipedia with a huge mess of packets. And this is what we call an amplification attack or a smurfing attack, where the point is to send a very small amount of content and then have the other, also essentially a victim, send messages at the victim. Broadly speaking, looks like this. So you send a ping down to this LAN. The ping goes out to every single one. It comes up with a response and sends the whole lot to the victim server. Yeah, this is a massive debate on the internet because this shouldn't happen. If you're doing your job right, you should just not let this happen. You shouldn't allow people to ping the insides of your network to start with. That's already a bad state. And then the fact that you're causing damage to other groups is also a problem. I am also focused on pings here because they're easy to understand. There's a lot of other protocols I could pick on that have a much bigger response. I don't think I have them on any of the slides, but there are several other protocols where I basically ask for, say, an entire directory, or I ask for a very large thing, and I just send the message. It goes out to the entire LAN. The whole LAN responds with these large network requests, all of which then hit the server, and then choke that bandwidth of the server. I'm also talking about doing this to one LAN. What if I just hit every single LAN on the bad LAN list all at the same time this way, and then again, I'm just sending a ton of traffic at that final server. All right, up to now I have done what was called DOS, denial of service. Most of the time, you've probably heard the word DDoS if you've ever heard this. It's almost always called DDoS. What I've just described is not DDoS, it is DOS, denial of service. DDoS is distributed denial of service. So a distributed denial of service is a large number of machines all working together to perform an attack. This used to be called a Slashdot effect. Is Slashdot still a thing? People are staring at me at blanks. Okay, I'm going to pick on Instagram instead, though. Well, no, it doesn't work. Drat. Okay, so Slashdot is a website. You can still load it. It has a bunch of news articles on it. It was very, very popular. So what happened is that somebody would go and have some fascinating video of painting the Firefox logo on a university or something, right? And then it would be posted on Slashdot, and this would cause everybody worldwide to access this tiny server that had this video on it all at the same time and take it down. We called it a Slashdot effect because we were more, when I talk about things like a Taylor Swift or a FIFA concert, those are big servers, hopefully. There's legal issues going on right now involving the Taylor Swift one not being a big enough server, but they knew traffic was coming. Versus imagine running your own little tiny web server and you post this thing you think is cute, and then suddenly it goes viral, and then boom. This is a non-malicious denial of service attack, a distributed denial of service attack. It is distributed because a whole bunch of different computers all accessed it individually. And that causes a problem, because if I want to stop traffic, if you think about all the way back to my initial attack, if I know the IP address of the attacker, what do? I shut them off. Or I call up their ISP and I say, can you cut this guy off? He's causing a lot of trouble. I can't do that when it's distributed. And that's why we see DDoS attacks being such a major issue. Common examples of Slash.fed, botnets. I have not talked in depth about botnets, but the entire idea is that I hack into a whole lot of computers, and then I send a message to every single computer saying, all of you, please try to visit this one website at the same time. And boom, down goes the website. I think this, I don't know if this is still a thing, Drat. So for a little while, China was operating what it called the Great Cannon of China. In order to do this, it was using the Great Firewall of China, and I will talk about firewalls in a few moments. But the main fact you need to know is that if you try and access anything from China, or you try to access anything in China, so any traffic passing into China, it goes through the Great Firewall, and the Great Firewall will go in and look at the content. And as we know, it is entirely possible to edit it. Man-in-the-middle attack. It's a big firewall. It can just check everything. It can look at it, and it can also edit it. So what it used to do sometimes is when they disliked a particular website, all the traffic that was going across unencrypted, that was a web page, they would man-in-the-middle attack it and just drop in a line saying, please access this web page. This looks a lot like the attack I showed you the other day with my student that was doing the cookie assignment and had their content attacked by the VPN. The Great Firewall of China used to just attack network connections and insert a JavaScript line just saying, please visit this website once a second. What happens? There's a lot of people in China. There's a lot of people who are Chinese that are not in China. There's a lot of content going across this. If even 1% of it is unencrypted, and that causes a connection every single second to a small website, boom. Basically, you're just pointing a whole lot of innocent people at this one website and just take it down. And this is a way of doing a distributed denial of service attack. This is the concept behind this. You'll see this concept keep coming up as we start talking about other ways of doing things. But the idea here is very simple. Let's just take a website down by going and just sending a lot of traffic at it. And that is a distributed denial of service attack. Okay, questions on that? I am going to a related topic, which is a firewall, which is one of the ways we stop these. DDoS attacks are very hard to stop. DOS attacks are much easier. Firewalls are very effective against DOS attacks. They are not so effective against the DDoS attacks. Okay. We're going to try to do firewalls in the short time we have. All right. We were talking about attacks. We are not talking about defenses. A firewall is a defensive tool. It's trying to protect you. It is not trying to attack anyone. I realize I just covered an attack firewall, but that's an abnormal behavior. A firewall is entirely trying to just prevent things from the internet from accessing your computer. Firewalls sound all fancy, and we talk about them very fancy, and big firewalls can be. But most firewalls are actually incredibly simplistic. They're basically a whole set of regular expression-shaped rules. And each piece of traffic that comes onto your computer, it's run through the rules. And based on the rules, it will either drop it on the floor or it will allow it to progress into the computer. So the idea here is that when a packet comes in, we run it against the firewall and we decide whether or not this packet can progress into the computer. Yes or no decision. Larger firewalls, like the ones that, for example, this university uses, probably have different rule sets. And so something will come in and it'll be sent to a rule set depending on where it is headed and what kind of thing it's meant to do. But their main point is they divide the inside of the network from the outside of the network. Here be dragons. Here be nice safe space inside the network. Castle security. Oh, okay. We also run firewalls for big networks, usually on dedicated devices. So every laptop in here is probably running a firewall. The firewalls that are being run for this university are probably sitting on a dedicated standalone server. We do this for a whole pile of reasons. What happens if someone hacks into our firewall? It is bad, because it means they can just turn open access to everything, and that is not good. So usually what we want to do is have the minimal footprint, principle of least privilege. We put the firewall on a computer that has nothing else running on it. If there is less stuff on it, our attack surface gets smaller. If there's less accounts on it, our attack surface gets smaller. If only one person can log into it and they have a 12-character password, that's a really small footprint. It is very hard to attack these. When you actually see an attack that successfully hits a firewall, it's usually very serious. I've seen, I think the last one I noticed was because someone hadn't updated their firewall software in 10 years and it took down an entire water treatment plant for a whole city. It was rather serious. So here's our sample network. You notice on our sample network here, there's this boundary firewall. It's just kind of hanging out here the entire time. And it's sitting usually behind the router. So the router might do a little bit of, okay, this is where it gets, I'm not going to get into depth in here. A lot of times firewalls are sitting on routers. I have put them separately here just for all of our own sanity, but often both of these do run together and they run in parallel. But the boundary firewall here is sitting kind of next to the router, and it's deciding, traffic can only get in if it has a port, if the router's willing to put up with it, and if it can get through the firewall. So let's look at just this bit. So we have the internet, the firewall, some computers. What happens is that questionable things come in from the internet. The firewall applies a set of rules. Here's a completely fake rule set. These rules are ordered because we want speed, network speed. And so what happens is a packet comes in and it tries to match to the first rule on the list. And it says, okay, this is a rule about TCP. Is this a TCP packet? Well, sure, this is a TCP packet. We don't care where it came from. It can come from anywhere. Is it going to this IP address? Where the IP address is specified as anything that starts with 192.168.1. anything. What destination port
and then it has a permit or deny. So if it's something's coming in here, then we allow it through, for example. And if it doesn't match this, let's say it's not a TCP packet, maybe it's a UDP packet, then we'll try to match it to the next rule. And it just cascades down like this. Firewalls make a lot of use of things like wildcard characters. We kind of talked about this in access control lists, so I'm not spending a lot of time on that. These are very similar to a router, isn't it? That's why they're co-located a lot. But it just throws stuff out. All right, here's the OSI network layer. It's come back to haunt us. So when we're processing traffic, we start at the application layer. We do a lot of stuff to it when we hit the base layer. We talked about how routers do actually undo bits of this. Firewalls come in a range of varieties. Some firewalls operate all the way down at the base layer. They're really only working on a singular packet at a time. They get a packet in. They're like, does this packet match? Yes, no. And they ship it on. But they don't have to. Whoops. Oh, this is just a random password rule set you can look at. I'm going to skip past this. So they could just process a singular packet at a time. That's totally possible to do. That is not how the Great Firewall of China works. Or they could do deep packet filtering. So we talked about TCP connections, or even TLS connections, but TCP in this case. Do I filter based on just the information in the packet header? And if so, maybe I can do this at a lower OSI network level. Maybe I can do it per packet. But maybe I need to do what's called deep packet inspection, which just means I have to reconnect the session. So maybe what I do is I look at this TCP connection and I reassemble the TCP. Keep in mind, TCP could not care less who it is communicating with. It just cares that the other server is out there and responsive. We didn't do a single thing on TCP around certificates, did we? So what may happen is this network router may actually reassemble all the packets and parse them up to part of the network, or part of the OSI network layer. It may put them together enough that it can do things like search for words. Now we're getting closer to what the Groot firewall does, because it cares about the words and things. And this is also true for things like email. So if your email server or email filtration has to reassemble the email, scan it for viruses before it progresses. It's not a firewall, but it's doing the same concept. It's taking in network traffic, it's reassembling it before dropping it back on the wire because it's scanning it for content. It can't scan things for viruses if they're encrypted or if they're broken into packets. So it has to reassemble them. And this is why we have a whole pile of these. We have packet filtering gateways, we have stateful inspection, we have application, and we have personal firewalls. So a packet filtering gateway is the simplest. It's operating around OSI level 3. It just looks at the source destination. It looks a lot like that table I just showed you. A stateful inspection firewall now has a sense of things like TLS or TCP connections. It also maintains information about what's going on in other connections. So a stateful inspection firewall may actually go, wow, I've just seen 20 of my hosts all connected from this same IP address, and that's weird. I'm going to shut that down. So it may be making decisions not just based on this stream, but based on other information it possesses. And so it's maintaining state. That's why it's called stateful. It's looking at how many different ports has this connected to. Are we looking at a port scan where a message is being sent to different ports just to see which ones are open? A stateful inspection firewall will go, look, I've just seen 40 ports all scanned. I'm going to shut you off. I don't care if you send it to a good port. You have your hand up?
No,
Okay.
I'm stretching, sorry.
This is to defend against things like a port scan. So the idea is your computer sends a message to every single port to see which one responds. Stateful, the base level firewall will not detect this. A stateful inspection firewall will, because it will record this information. That's what things like this are doing in this rule set that I kind of skipped past earlier. The idea is you have these rules, and some of the rules say things like whether or not this is a new connection. How does it know it's new? Because it maintains state. You can also have an application proxy firewall. This is one that's actually reassembling all the packets and then passing them up pretty high actually in the OSI, possibly all the way up to 7, the top layer. This is the example I was giving about email, for example. Or maybe I reassemble an entire web page, I scan it to see whether or not it has any viruses in it, and then I send it back on into the inside of the network. Whenever you're looking at a lot of scanning for viruses and things, you're probably looking at something that's closer to an application proxy. This allows the administrator to block certain types of requests. It allows, for example, to block traffic with certain words, remove Word files, prevent anything that looks like a credit card number from leaving the database. Anything like this requires reassembly of the packets. A personal firewall is not stronger, it's just personal. It's usually not strong enough to do most of these other things. So it usually is running on your computer. In modern software, it's usually part of a suite. So you'll have like the firewall, but you've probably actually paid for an antivirus, and then the firewall has come with it, because firewalls are fairly simplistic devices. And so it's possible that the antivirus and the firewall, if made by the same company, are working together to do these sorts of scanning before anything enters your machine. We are obviously not doing that because we are out of time.
What does deep packet inspection even mean in the
It means reassembly. Deep packet inspection means that they have reassembled the packets.
So the answer is that the email server does it anyways?
Deep packet inspection is easier to do on email because email is just raw text. So if you imagine something that's being sent across gzip, for example, I need to be able to reassemble the gzip in its entirety to unzip it in order to scan it. So that means I really do have to go up the entire stack. With email, because it is solid text, you're still going up the whole stack, but the distance up that stack is much shorter because you're just reassembling text. It is also, if you're trying to scan for a word, it's possible. Okay, I'm just checking. All right. This is one of the things that the Great Firewall does. Sometimes it will just allow the traffic to go through, it not reassemble them, but scan it for words, because you can scan for words. The moment it sees a word it doesn't like, it drops a FIN packet in and terminates the TCP connection. And then only part of the website makes it through, and most modern browsers will treat this as if it was a problem and just terminate the entire connection. And so whenever you're scanning for words, you can actually do it without as much state. And I think that's where I am. Okay. I will not be covering DNS. This is a mini version anyway. I will cover it during the point where I actually properly cover it in web security. So, yay, we are done with networks. What are we working on next? I think it's secure programming. Okay. Here are the end of networks. I will be pushing out a couple games and hopefully an assignment associated with this shortly. The TA has escaped. Sorry, she's in the middle of trying to set that up right now.
You should be able to find her in her office.
Yeah, I can find. She's a nice TA. Don't worry. But anyway, all right. I will see you. It's Friday, Monday.
I'm surprised that you are surprised about there actually being internet police in Congress.